Hey everyone, and welcome! Today we're going to tackle a force that is literally everywhere, from the tip of a tiny nail all the way down to the crushing depths of the ocean. Okay, let's jump right into the fascinating world of pressure. So, I want to start with a question that sounds a little weird, right? What could possibly connect a nail with the bottom of the sea? Well, the answer is the single incredibly powerful concept in physics. And by the end of this, you're going to see exactly how these two very different things are linked. All right, let's kick things off with a little puzzle. Imagine you take a hammer and you whack a bowling pin against a wall. What happens? It just bounces off, right? No big deal. But now, take that same hammer, use the exact same amount of force, but this time, hit a nail. It sinks right into the wall. So what's going on here? I mean, if the force is identical, why is the result so completely different? There's obviously some kind of secret ingredient at play here that we're missing. And here it is. The secret isn't about how much force you use, it's about how that force is spread out, how it's distributed. You see, with a bowling pin, that force was spread over a big, wide area. But with the nail, all of that same force got focused, really concentrated, onto that one tiny, sharp point. And this whole idea of concentrated force has a name. We call it pressure. The official definition is just the amount of force you exert divided by the area you exert it on. Or, as you'll see it in physics, P equals F over A. So a really small area, like the tip of a nail, creates an absolutely enormous amount of pressure. Okay, this brings us to a really famous and, let's be honest, kind of terrifying thought experiment. If a single nail creates so much pressure that it can pierce a wall, how in the world could anyone possibly survive lying down on a whole bed of them? Well, this is where our intuition gets flipped completely on its head. See, your body weight, that's the force. But that force isn't on one nail. It's distributed across thousands of them. When you add up the area of all those little nail tips, the total area is actually pretty big. And a big area means the pressure from any one single nail becomes super, super tiny, way too small to even break your skin. So yeah, it's not magic, it's just physics. So we've kind of figured out how pressure works with solids. But what about things that flow, like liquids and gases? Let's dive a little deeper into the world of fluids. So to wrap our heads around this, let's just do a quick thought experiment. Picture a can of beans sitting at the bottom of a swimming pool, okay? Now, all of the water that's directly above that can forms a weight column, right? And that column of water has weight, thanks to gravity, and that weight is pushing down, creating pressure on top of our poor can of beans. So how do we actually calculate that pressure? Well, we can build the formula for it piece by piece. We always start with what we know. Pressure is force over area. Simple enough. Now, what's the force here? It's just the weight of that water column, which is its mass times gravity, g. Okay, next step. We can rewrite mass as density. That's the Greek letter rho times volume. And the volume of that water column, that's just the area of its base, a, times its height, h. So when we mash it all together, we get that awesome-looking expression you see in step 5. And now for my favorite part, check this out. The area on the top and the area on the bottom, they just cancel each other out. It's so clean. And it leaves us with this beautiful, elegant little formula. Pressure equals rho GH. What this means is that the pressure at any depth only depends on 3 things: the density of the fluid, gravity, and how deep you are. It doesn't even matter what the object is. Now, of course, water isn't the only fluid that pushes down on us. In fact, right now, all of us are living at the bottom of a giant ocean, an ocean of air. And guess what? It has weight too. I love this quote. It paints such a wild picture. The only reason we don't feel all that air pressure is because our bodies are pushing back with an equal and opposite force. But if some space pirates tossed you into the vacuum of space, well, there'd be no air pushing in, and all that pressure inside you would still be pushing out. And we're not talking about a small amount of pressure either. At sea level, the atmosphere is pressing down on every single one of us with about 101,000 pascals. That is a huge number, and it's there all the time, every single second. So, because of this constant atmospheric pressure, we actually have 2 different ways of talking about it. The first is gauge pressure. This is what you measure with, say, a tire gauge. It's the pressure above what the atmosphere is already doing. The other is absolute pressure, which measures all the way from a perfect vacuum and includes the atmospheric pressure. And the good news is the connection between them is super simple. The absolute pressure is just whatever the gauge pressure reads plus the atmospheric pressure. That's it. Nice and easy.
All right, that's enough theory for now. Let's get our hands dirty and actually apply these formulas to a couple of real-world problems. First up, we've got this fuchsia chair. Its weight, its mass times gravity, is the force, and the area is the combined area of its four little feet. So we just plug those numbers into our good old P equals F over A formula, and we find out the chair exerts about 33,200 pascals of pressure on the floor. Okay, that was pretty straightforward, so let's turn up the heat a bit. How much force do you think is pushing on a tiny submarine window when it's deep under the ocean? Now we're talking about some serious fluid pressure. Here's all our data. We know the depth, her, we know the density of seawater, rho, we know gravity, g, and we know the area of that circular window. Looks like we have everything we need to solve this thing. Now, pay attention here. The question is asking for the total force, not the pressure. So we go back to our basic definition, P equals F over A, and we just rearrange it to solve for F. That means force equals pressure times area. And since we're in a fluid, we can just swap in our fluid pressure formula, rho GH for P. And when you crunch all those numbers, you get a staggering 6,230 newtons. To put that in perspective, that's like having an entire grand piano sitting on that one little window. It just goes to show you the incredible power of fluid pressure. So let's do a super quick recap of what we've learned. Pressure is just force spread over an area. In fluids, that pressure gets bigger the deeper you go, following P equals rho GH. We're all living under constant atmospheric pressure. And using these simple, really elegant ideas lets us figure out some absolutely massive forces in the real world. You know, we've spent all this time talking about how pressure pushes down, how it crushes. But buried in our source material was this little hint that a difference in pressure can actually create a net upward force. Which leads to one last big question. What exactly is this buoyant force? And how is it possibly strong enough to make a massive ship made of steel float on water? Well, that's a great story for another time.